Before we move on to hypothesis testing, wanted to cover a few terms again. Quick recap. So before we go on, students must be very clear between the distinction and the importance of these terms. What do we mean by population mean, sample mean, population standard deviation, sample standard deviation, and standard error of the mean? So whenever we are talking about doing any analysis or doing any kind of a data inference, we are almost always working with samples. So we always have the measurement of the sample. It could be the sample mean, which is x bar. X bar is not the population mean. It is approaching the population mean. It approaches mu, but it may or may not be close to mu, depending on the kind of sample, how big is the sample, and what is the standard error of our sample. Going back again, the population standard deviation. So we will not have the population standard deviation. We will almost always have the samples standard deviation. The sample standard deviation is denoted by the letter S, whereas sigma refers to the population standard deviation. The population standard deviation is not known to us, so we typically always get the sample standard deviation. And coming up to the standard error of the mean. Now, standard error of the mean is neither the population standard deviation nor is it the sample standard deviation. Standard error is the distribution of the sampling, is the standard error of the sampling means that we've extracted, i.e., if I extract a selection of samples from the population, right? So I have sample 1, sample 2, all the way till sample n. Therefore, I have a variable which is got the means of each of these samples. So I'll have n number of observations in this sample. Then these n number of observations will follow a normal distribution as per the CLT. And the mean of these samples will approach the population mean as per the CLT. And the standard deviation of these sampling means is the standard error of the mean, which is the error in our estimate of the population mean given a sample. So the way to calculate the standard error is always the sample standard deviation divided by under root of n, where n is the number of observations. We are always having the sample standard deviation, and with the sample standard deviation I can always calculate the standard error. Alright, so we wanted to quickly recap these terms before we move on to hypothesis testing. So moving on to hypothesis testing. What do we mean by hypothesis testing? How do we actually formulate and test a hypothesis? How do we test the statistical confidence of a particular hypothesis? I'm going to cover these points in the coming lectures now. Now, how do we go about doing hypothesis testing? So I'm going to start working with a example. So let's say I have a hypothesis that just hold on, let me create the screen well. Yeah. So I have a hypothesis which says that the average, let's say the average income of households, sorry, let me just make the spelling better, households in city X is 10,000 units of that currency, right? This is the annual average income of that city X. Now, how do I test this hypothesis? This is only an hypothesis. This is not the actual average income, right? So I make a statement that the average income of the households in city X, and we have a survey of all the households. We don't have the average income for them, but we know all the households in the city X, and I say this is 10,000 units of that currency. Now, how do we test this hypothesis? Is this hypothesis true? Is it false? Is it close to the truth? Is it within a is it 95% true, or how do I come up with a range which is likely to be 95% true? The answer you might say is that we can go and ask every household in the city what is their income, add it up, do an average, and you will get the exact number. So that is that is actually going out and asking the whole population. That may not be the correct way, or they may not be cost effective. A simpler way is that can I extract an SRS of the households in the city, which is a simple random sample? once I extract a simple random sample, right? Let's say I extract a sample of 1000 households, right? And the average income for these 1000 households comes out to be 11,500. And the standard deviation for this, so this is the sample mean. I'm going to call it SM, which is the sample mean. And the sample standard deviation, SSD over here, comes out to be, let's say, 700, right? And the N over here is 1000, which is the number of households that I've taken out. Now using this, can I test the claim that I made the claim that the average income of the household is 10,000? Is this claim true or false? You might say, looking at this, that the sample is coming out to be 11,500, therefore this claim is false. But are we sure this claim is false? Can we reject this claim with a 95% certainty that this claim is false? Right? In this case, we can go ahead and do something known as a hypothesis testing. And I'm going to show how does hypothesis testing work and how we can actually test this claim at a confidence interval of 95% or 99% or 50% or whichever number that we select. So let's take up this exercise in a fresh sheet, right? So the exercise maintains that we want to test claim, the claim or hypothesis. Hypothesis is that the average income is 10,000. Now I want you to apply the central limit theorem. This says over here. So central limit theorem says that irrespective of the distribution of the income in the city, if I extract samples, the sample means will follow a normal distribution and the mean of the sample mean will start approaching 10,000. So assuming 10,000 is the population mean. So we're going to start with the hypothesis that the average income is actually 10,000. Therefore, if it is actually 10,000, right, and I track income over here and I track probability over here, right, so let's say this is at 10,000 or 10k level, then the samples that are extracted from such a population are going to fall on the normal curve. Let me just right shift this normal curve a little. Sorry. So this is the 10,000 level, right? So I'm going to have a normal distribution centered around 10,000, right? So this will be the sampling distribution or the range of samples that I can extract from such a population. Therefore, given if compute the standard error of the mean, right, then within 1.96 standard errors of both sides, if I take 1.96 standard errors on both sides, so 1.96 standard error here, 1.96 standard error here, right, the shaded region will give me 95% of all the samples I extract from such a population. 95% of sample means will lie in this region, which will lie between, let's say, the lower confidence level and the upper confidence level of this mean, right? So if I compute the standard error of a sample and I apply it to this particular hypothesis, I can check whether the sample is likely to come within 95% region of this or not. So if it comes within this region, I call it the acceptance region, right? Then I accept the claim that the population mean may actually be 10,000 because the samples are coming within the 95% probability region of 10,000. But if the samples lie in this region or in this region, right, they are coming on the outside region, that means such a sample, while it can be extracted from a population of mean 10,000, but it is highly unlikely, right? So there's less than 5% chance or 2.5% chance here, another 2.5% chance here, that such an extreme sample can actually be extracted from a population of mean 10,000. Not to say it can never happen, it can happen, and in 5% of the cases it will happen, but in 95% of the cases it will not happen. Therefore, if my sample mean lies in the 95% region, I say, what? This claim may be true, right? Such a sample is quite possible. But if the sample is such an extreme value or away from 10,000, it is more than 1.96 standard errors away, it lies in this 2.5% region on either side, right? Then I can reject the claim and say, you know what? There is less than 5% chance that we have extracted a sample such that the population is actually 10,000. The population may be something else. In this case, we can go ahead and reject the claim. Right? So this is at heart how I am going to apply the central limit theorem to actually test this claim. Now going back to a previous example where we had a population mean, sorry, a sample mean, right? So I'm going to again draw this out over here. So here we go, right? The population mean hypothesized is 10,000. Check this claim and let's say 95% level, right? The sample mean, I've forgotten what I gave in the example. I think I gave 11,500, right? And the sample standard deviation came out to be, let's say it was about 700, and the size of the sample was 1,000 households, right? So first thing first, I'm going to formulate something known as the null hypothesis. It's pronounced as the null hypothesis. So the H naught, it is called the H naught or the null hypothesis. The way the null hypothesis works is whatever is the claim being made, in absence of proof, that claim is assumed to be true, right? Unless there is proof otherwise, whatever we are testing is assumed to be true till the point we've disproven it, right? So we are going to start with the null hypothesis. Yes, that we've made a claim that the average income is 10,000. So H naught is that, the population mean for average household incomes is 10,000 units. Then we formulate something known as the alternative hypothesis. What would happen if the null hypothesis is wrong? So I call H naught as the null hypothesis, HA as the alternative hypothesis. The alternative hypothesis is always the exact opposite of the null hypothesis. So in this case, the null hypothesis says that the average income is, let's say, 10,000. Therefore, the exact opposite is that the average income or the population mean is not 10,000. Right? So this is the exact opposite. We don't say the H naught is that average mean is greater than or less than 10,000. That's not the exact opposite. The null hypothesis that we are testing is that the population mean is 10,000 units or currency earned. The alternative hypothesis is the average income is not 10,000. Now applying the central limit theorem over here, right, that if this particular sample lies within 1.96 standard errors from the population mean, right, then that means that there is a 95% probability that such a sample can in fact be extracted. That means that the difference in the means, it is the sample mean is 11,500, hypothesis is 10,000, the difference is 1,500. Such a difference can happen due to the sampling error. But if this difference is larger than the difference that can happen within 1.96 standard errors, we can say, that the population mean is likely to be something else, because such a sample is unlikely to come from a population of mean 10,000. Therefore, the difference in this has to be divided by the standard error, right? So going back to a previous lecture, standard error of the mean is calculated as the sample standard deviation divided by the under root of n. So in this case, sample standard deviation is 700 and the number of observations is 1000. So 700 divided by under root of 1000. So which gives us, so I'll just pull up the calculator, which will give us an exact number. So 700 divided by, I'm going to open the bracket here, square root of, so where is the square root function? Okay, so I'll just raise it to power 1000 raised to power 0.5. Okay, I did something wrong, just hold on. Yeah, there's the square root function, so let me try it again. So sorry. So it's going to be 700 divided by the square root. Okay, it's gone wrong again. Let me clear this. Yeah, just let it be multiplied by 0. Man, teaching analytics course and I don't know how to use this calculator. I'll just close it. And you know what? I'm not going to even edit this video or let it be so you can know how big anyhow. So 700 divided by the square root of 1000. I don't believe this. Let me just go do it on Excel. I use Excel more than I use a calculator anyhow. So the standard error is going to be 700 divided by the square root of 1000. It's not a good day for me. And which is 22.1359. So I have a standard error which is equal to 23.159. Yeah, 23.135, sorry. 13. So which is essentially saying that if I calculate the number of standard errors which separate the two hypothesized means, so I take the hypothesized mean was 10,000, the actual mean is coming out to be 11,500, and I divided by the standard error which is 23.13. This gives me about 1500 divided by 23.13. Let's calculate this value exactly, which is equal to 1500 divided by 23.13, which is about 64.85, which is a very big number. So this comes equal to 64.85. So if I calculate this again, let me just pull up another sheet. So looking at this hypothesis again, it shows that in a hypothesized environment where the population mean was 10,000 and I've extracted a sample which is 11.5 thousand or 11.5k, the difference between these two in terms of standard errors is coming out to be 64 standard errors. So this particular mean is way outside the acceptance region of a 95% interval level, right? So within 95% interval level is about, so the standard error is 23. So if I have 10k as the sample mean, in most cases, in 95% of the cases, 95% of the sample will be 10,000 plus or minus 1.96 into 23.1. So in 95% of the cases, the sample I extract from a population mean of 10,000 will lie within this particular range. That is 10,000 plus minus 1.96 into 23, or to be a little bit close, about 23 into 2, which I do is about 46.2. Yeah, so it will come very close to this number. So so a population of mean 10,000 is likely to give us samples which will range plus or minus 46.2 from this figure for 95% of the cases. The sample that we've extracted is 11,500, which is way outside of the acceptance region, which is about 64 standard errors and not just 1.96 standard errors. So such a sample is highly unlikely to come from a population of mean 10,000. Right? Therefore, we are going to reject this claim. So we are going to reject the null hypothesis. And once we reject the null hypothesis, we are going to go with the alternative hypothesis, which says that the population mean is not 10,000 because the sample that we've extracted rejects this hypothesis at a 95% level. Right? So if I want to be 99% sure, how do I check it? If I want to go 99%, then I need to go more than 1.96 standard errors. Then I need to go about, if we look at the Z table, we need to go about 2.57 standard errors up and down, right? So this is how we actually do a one sample significance testing, and that's how we go to approach a Z or a T test. So more on that little later. I'll quickly recap the procedure to do a hypothesis testing.